In this short video, in today's class, we're gonna cover a new topic, which is also popular machine learning topic. It's called shrinkage. If you took a data science computing class, you may already see some examples about this. It's called ridge regression. And lasso regression can be used for the subset feature selection. Feature selection. And also another one is called lasso regression. Okay, so first let's talk about the ridge regression. It's relative close, just one extension of the linear regression. Okay, so ridge regression. It has another name. It's called Tikhonov regularization. Okay, the basic setup is assumption is that we have the least square linear regression. And plus L2 penalized mean loss. Okay, the basic setup is we have the regression. We have the loss function is A plus the cost function, mean squared error loss, plus the optimization is we use D. I'll give you as you recall from our lecture 10. So what's one here? One is the, if you go back to our basic setups for the regression. So first part, we use the linear regression. So the regression function is the linear regression format. Okay, so one is linear regression. And the loss is a squared error loss. So loss is y minus z square. Okay, maybe I should use the parentheses here. And the cost function is the average cost, average mean loss function. So mean loss. And the optimization cost to minimize is the cost function to minimize is the you be not we also have a penalty term. So plus a penalty term. Okay, so I will give you more details next. So first, before even we talk about the ridge regression or lasso regression, first you need to understand why do we even care about this ridge regression? Why do we need regularizations? There are several motivations. So the question is, why do we add this penalty term? Add a regularization term. Actually, if we summarize what we're trying to minimize, remember if for the linear regression, we only have the first three, right? For the linear regression, actually, we are trying to find the weight, W, that minimize the mean squared error loss. So which means if we use a matrix, design matrix times the coefficients W minus Y is a vector, so we take the norm, take the square. So it's mean squared error loss. But here we need to add a penalty term, which means we plus a lambda times the W prime square. Okay, so what's this W prime? W prime is W with intercept term replaced by 0. Okay, so we only penalize the coefficients of the x. So suppose you have the, maybe let me elaborate here a little bit more. So in the regression, so we have the yi equals to alpha intercept plus x1 I1 times w1 plus xi2 w2 and up to xid wd, right? So this w prime only contains w1 to wd. There's no, and the first term will become to 0. Remember when we write down the design matrix, we can written this as xi1 xid. Okay, multiply the and when we design the design matrix, we add a constant 1 term at the end. Do you remember? Add 1 term here. Okay, and then we multiply the weight matrix. So weight vector w1, w2, wd, and the last one is alpha. Okay, so this is our w vector, but w prime here we want to penalize on the coefficients on the covariates only. We do not want to penalize on the alpha intercepted. Okay, so that's the problem we are facing now. So we are trying to find a weight W that minimize this cost function. So actually think about what this will do. Okay, so actually this large lambda will encourage small w. Okay. Actually, there's so if you think about the minimization problem, if you give the constant multiply the length of this w, so a large lambda will encourage the small w. So why do we give this regular? This is called regularization. So why do we even want to add this regularization? Is because there are two motivations. Okay. Motivation one. It guarantees positive definite normal equations. Positive definite normal equations. So for example, in this plot, we can have this you can think this is a cost function here. So x w minus y, okay? And this is a contour plot for this normal equations. But as we can see, the minimizer for this, so if this quadratic form is positive definite, we have unique solution. But some cases, we may not have the unique solution. For example, in this case, the whole diagonal line is a minimizer for this equation. So in other words, if this happens, all the W1, W2 on this diagonal line will be the solutions for our linear regression. So we lost the unique solution, okay? But if we add a normalization constant, we add a regularization term, this will be the contour plot here. So this will make our contour plot to be eclipse, to be more convex, such that the solution is unique. Minimizer is unique. Okay, so that is the first solution. Okay. Sometimes this is called the regression problem is ill-posted. So this regression, if your solution does not have unique solution, so this is said regression is ill-posted. So by adding a small penalty term, we obtain positive definite quadratic form, which is shown on the right hand side, and with unique minimizer. Okay, so regularization implies that we are turning an ill-posed problem to a well-posed problem. So that was the originally motivation for the ridge regression. Motivation 2. Okay. By adding this regularization term, we can reduce the overfitting. By reduce the variances. So last class we talked about the decomposition of the cost function of the general modeling. One component is the variance of the model, right? So by adding this regularization can reduce the variance, model variance. So here is one example. So suppose we have the data x1 is just the origin point. So we suppose we only have this is the toy example, and the corresponding label for y1 is equals to 0. Okay, x2 equals to 1 and 1, and y2 is equals to also label 0, and x3 is equals to 0.51, 0.49, and the label y3 is 1. Okay, so in this case, let's see, the linear regression gives the perfect fit. For example, if we have the regression y equals to 50 times x1 plus minus 50 times x2. Okay, so this hyperplane, this will be a hyperplane. This hyperplane goes through every observation point. For example, if you plug in 0, 0, you get 0. Plug in 1, 1. 50 minus 50 is 0. If you plug in the last one, for example, 50.51 minus 0.49, this equals to 50 times 0.02, and which gives you 1, right? So by using the linear regression, it fits these 3 data points perfectly. But the problem is this model has high variance. Because if you give a little bit perturbations on the x1 or x2, it will change the result a lot. For example, if you change the x1 from for example, if you change the x1 from 0 to 0.5, okay, x only change a little bit, but the x1, this term will change like a 25 scale, right? 50 times 0.5 is 25. So you alter the x1 a little bit, the regression function will change dramatically. Okay, so the weights in this weights is so big. We have the big weights here. Would be justified. This large weights implies that tiny changes in x can cause huge changes in y. Consider that a label don't differ by more than 1. So here we only have the label between 0 and 1. And the points are separated by a distance greater than 0.7. So the disproportionately large weights are a sure sign of overfitting. So we penalize the large weights. So that's another motivation. So we want a regression such that this coefficient can be relatively small. So this use of regularization is closely related to these are the two motivations of where the ridge regression are originally derived, but now it's became very, very popular in the machine learning area. And the second motivation shows that if your model has large variance and a lot of the overfitting, it implies your problem is close to ill-posted. Okay, so even though we can find a good solution, but if you change the x little bit, you don't have solutions. Okay, so that's the motivations for the ridge regression. And I will give you 2 more plots here. Where this ridge regression solution come from? So now the problem is how to solve the ridge regression solution to ridge regression. Okay. Remember, our ridge regression problem is to solve the minimizer for this cost function. Actually, this is our j, right? This is our j. So cost function. So by setting the gradient of this cost function equals to 0, this gives the following equation. So it's sort of relative close to the solutions to the linear regression. So remember, in the linear regression, our solution is x transpose x times this w equals to x transpose y, right? And then we take the inverse of this term, we get our solution for linear regression. But here, little bit different is that we plus lambda times identity matrix and times w equal to 0. This identity matrix is the first d terms are 1 on the diagonal elements, and the last term in the diagonal elements is 0 because it's corresponding to 0 for the intercept. We do not give the regularization on the intercept. Okay, so and this will give us a solution. You solve the linear system, so you get the solution is equals to w equals to x transpose x plus lambda I transpose I prime inverse x transpose y. Okay, so this will be the solution for the ridge regression. In a linear regression, it's not necessary that we have this x transpose x to be invertible, but here there's note. X transpose x plus lambda I prime will always be positive definite. Positive definite. For lambda greater than 0. Okay, so you have the, so this term will always invertible. Okay, so ridge regression will always give us some solutions. Maybe let's see what's the solutions for this minimization looks like. Okay, so first let's check the SO contour plots for this original. This is the cost function for linear regression. Okay, without this, you can ignore this blue line first. So without this ridge regression panel regularization, this is a contour plot. Okay, and this is this red dot in center is a minimizer for the linear regression. Okay, originally the solution is relatively big. And the second term, the penalization, this is lambda times w prime norm. So lambda times w norm square equals to constant c. Okay, this is drawn on this circle. So for example, if we think w is only a two vectors, let's ignore the intercept first, w1, w2. Okay, so see the w1 square plus w2 square equals to some constant c will give us this rich solutions, will give us the isocontour plots for the w square, isocontour plots for the w square. So they are circles, and the solutions is occurs when you have the original linear regression solutions, but now you have the restrictions. Your solution should be lie on these blue circles. So originally this is the solution, but now after you give the regularization, depends on how large lambda you want to give. It restricts your solutions to live on these blue circles. Okay, and so this shrinkage, the larger lambda value is, the bigger shrinkage we have. Okay, so it will ultimately, if you give the lambda equal to infinity, it will give all the weights to be 0, which means all the coefficient to be 0. If you give smaller lambda, it's more close to the original solution. So when lambda equal to 0, there is no penalization, no regularization. So the solution will be same as the original least square regression. If you give lambda equal to, set lambda equal to big values, you give more regularization, so you drag the solution more close to the origins. And then if you have the lambda equal to infinity, you give the huge penalties on the large w, so your solution will close to 0, 0. Okay, so that's the idea of the rich regression. So in summary, the algorithm to solve rich regression is you do the followings. First, solve w equals to this x transpose x plus lambda I prime inverse x transpose y. Okay, you solve this w first. Second, you return your regression function will be hw equals to x transpose. Maybe we should not use w here. This is the regression function, should be input is the feature space. So this should be return. Suppose our new feature is z equals to z transpose w. Okay, and note, increasing lambda so implies more regularization. And smaller the length of the w, so smaller weights. Okay, And why this reduce the model variance? Because so this implies model variance will be smaller. Okay, this is because our linear regression is like y equals to x times this w plus some error term, right? So the variance of this model, the variance or our model H, will equals to the variance of this design matrix times w plus epsilon. And the epsilon is the error term. That's the constant part. So this equals to the sigma square is the variance of the epsilon plus the variance of the first term. So after I will just show you some results. Actually, the variance of this formula will our model will equals to the variance of the of x transpose our design matrix x transpose x plus this is the training data, this is new data. This is this x is design matrix plus lambda times I prime take the transpose x transpose times this epsilon. Okay. So this is the inverse because this is the solution part, right? Solution part. So you can think this is variance of the flip of this scalar lambda. So the larger lambda is, this will make the variance smaller because lambda you can think is in the denominator of this variance term. So the larger lambda will give us smaller variance. So here is one example. If we change our hyperparameter lambda in the ridge regression, what's the variance gonna go? So if you increase the lambda, the model variance will decrease. But we know the testing error is a summation of the variance plus the Bayes square plus that irreducible errors, right? That irreducible error we cannot change. So the variance, so the test error is the summation of the variance plus the Bayes. So so as we can see, this lambda, when lambda increases, okay, the model variance decreases due to this, and but the model Bayes will increase because of regularization, right? And actually, the best model we can search is we need to find out the point where the testing error is smallest. So in application, we're gonna use cross validation to find this the perfect lambda. So this lambda can be seen as a hyperparameter to tune such that the testing error is the smallest. So we can reduce the overfitting. So we make the variance decrease, we reduce the overfitting. So lambda usually is determined by is a hyperparameter. Can be tuned by cross validation. Okay. I think that's about regression. So next, I will ridge regression. Next, I will talk about the Bayesian justification for the ridge regression.